In this lesson, we're going to move beyond the basics of Lewis dot structures. Before we do that though, please draw the Lewis dot structure for SiBr4, silicon tetrabromide. Pause the video and do this now on your note sheet. Silicon is in group 4A and has 4 valence electrons. Bromine is in group 7A and has 7 valence electrons, and there are 4 atoms of bromine. So we're going to take that 7 and multiply it by 4 for a total of 28 electrons for the bromine. Altogether, that is 32 electrons that we're going to put in our Lewis dot structure. The less electronegative element goes in the center, and usually it's the element that's all by itself. And then we're going to attach the bromines to the central atom. They're going to each share a pair of electrons with the silicon. And so now silicon has its octet, it has access to 8 electrons. And now the bromines need their octets. Each bromine is going to get 3 lone pairs of electrons. When you're all done, count the total number of electrons that you have in your Lewis dot structure. It should match your total number of valence electrons, which this one does. And everything has its octet. So now we're going to move beyond the basics of Lewis dot structures and talk about some exceptions to the octet rule. Usually we're looking for each atom to have 8 electrons to fill the s orbitals and the p orbitals. However, there are some atoms that do not need 8 electrons. I've given you the examples that I need you to know here. The most important one will be hydrogen. Hydrogen doesn't need an octet, it only needs 2 electrons. You can call that a duet of electrons. Hydrogen is in the first period of the periodic table. Only 2 electrons required to fill that energy level. And then there are some other atoms here which you would say, oh, I see a lot of metals here, right? Like beryllium and magnesium and aluminum. But sometimes you'll see some exceptions and you'll have some polar covalent bonding with metals. But probably the most common one you would see is going to be that boron, so that metalloid boron there. So beryllium and magnesium, if you see them in a covalent compound, they only need 4 electrons. Those are both in group 2A. And boron and aluminum needs 6 electrons. They are in group 3A. So you got to know these. When you see them, you have to recognize that we're not going for an octet. So now we're going to draw the Lewis dot structure for BF3. Notice that boron there. That's one of those exceptions to the octet rule. So when we put boron in the center and we bond it with the fluorines, it has access to 6 electrons. So that's done. Okay, so boron has 3 valence electrons and fluorine has 7 valence electrons, and there are 3 of those atoms, so that's 21 electrons. Altogether, that's 24 electrons total that we'd like to see in our Lewis dot structure. So that boron is all done. It just needs 6 instead of 8, but fluorines will still be normal and give them their octets. So 3 more lone pairs for each fluorine, and then when you add that all together, you will see that is 24 valence electrons total. There are some atoms that will take more than 8. I don't think you really need to memorize or know any of these. It will become very obvious when you draw them out. I've given you some common examples here. There are others, but let's do one that has sulfur in it, SF6. So sulfur, group 6A, 6 valence electrons, and fluorine, like we saw in the last example, 7 valence electrons. This time there are 6 of those fluorine atoms. Altogether, that's going to be 48 valence electrons total. So we'll put sulfur in the center. It is less electronegative than fluorine. And then we're going to attach the 6 fluorines. So see how it becomes obvious that we're going to have an exception here. Sulfur is actually going to have access to 12 electrons. Draw those fluorines in there. And now fluorines are still normal. So octets for all the fluorines. And here they are. Add up all those electrons. That does add up to 48 valence electrons total. Let's look at SF4 now instead of SF6. So again, sulfur, 6 valence electrons, fluorine, 7, and then times 4. Altogether, that is 34 valence electrons. Sulfur in the center, attach those fluorines, and then give the fluorines their octets. So now if you count up all these valence electrons, you'll see you only have 32. This is why it's so important when you're done to double check and make sure you have the right valence electron count in your structure. So it says here that if the number of electrons added is less than the number of valence electrons allowed, the excess electrons are added to the central atom, and we're going to draw them in as a pair. You can put them anywhere. I'm going to put them right here. So you can see once again it becomes obvious that sulfur is an exception to the octet rule. It has access to 10 electrons total. We can also draw Lewis dot structures for polyatomic ions. So a polyatomic ion is a bunch of nonmetals. They are covalently bonded together. They do overall carry a charge, and we saw those with the ionic compounds in the last unit. And if you remember, we can have negative or positive polyatomic ions, mostly negative, but that's going to affect our count for our total number of valence electrons. So if we have an anion with a negative charge, we're going to add the electrons that are equal to the charge to the total number of valence electrons. And if we happen to have a positively charged polyatomic ion, we're going to subtract those electrons from our total number. So remember, something with a positive charge, a cation, has lost electrons. So you have more protons than electrons at that point. And so then when we're all done, when we've drawn out our structure, we're going to draw a set of brackets around that structure, and we're also going to indicate the charge. So we're going to tell everybody we added or we subtracted these electrons. We've got SO4 here, which is sulfate. So sulfur, 6 valence electrons. Oxygen, 6 valence electrons also, both in group 6A, and then times 4. And then we have a -2 charge. And so that means 2 extra electrons. So we're also going to add in 2 extra electrons to our total, and that's going to be 32 valence electrons total. Sulfur goes in the center. Attach those 4 oxygens. Give the oxygens their octets. Double check your number of valence electrons. It should be 32, which it is. And then for polyatomic ions, a set of brackets around the structure, a big set of brackets, and then put the charge. So you're telling everybody I added in 2 extra electrons to SO4. That's why I have 32 valence electrons total. And by the way, notice here that sulfur is just a normal octet, whereas the previous 2 examples that we looked at, we had sulfur with an expanded octet, so more electrons than 8. But sulfur can also just be normal and have a normal octet. Okay, so now let's move on to multiple bonds. This is probably the trickiest part of Lewis dot structures. So far we've been drawing in single bonds, so atoms sharing just a pair of electrons, 2 electrons, but atoms can also share 2 pairs or 3 pairs of electrons. These are called double or triple bonds, and generally we call this multiple bonding. There are elements that most commonly do this: cons, carbon, oxygen, nitrogen, sulfur. But just because a molecule has these elements doesn't necessarily mean you're going to have multiple bonding. What you want to do is draw your Lewis dot structure normally, paying attention to that octet rule. And then when you're done and you're double checking your number of valence electrons, you're going to find that you have too many electrons in your Lewis dot structure. So the number of electrons added to the structure is actually greater than the number that's allowed. So then we're going to modify the structure and put in some multiple bonds. I'll show you here with nitrogen. So this is like the nitrogen that's in the air that we breathe. Nitrogen is in group 5A, and 5 valence electrons times 2, that's 10 electrons total. If I draw nitrogen out normally, No central atom here, right, because they're just two atoms, but I'm going to give everything its octet. And if I count this up, I'm going to see that that's 14 electrons. And that's too many. So that's where multiple bonding comes in. You're all done, everything has its octet, and you just have too many electrons. So now we need to modify our structure. We're going to take one pair off of each atom. Doesn't matter which pair of electrons I choose, just take one pair off of each. We can't have all these lone pairs, we have to have more shared pairs instead. I'm going to draw in another dash there. That's a double bond. So now we'll double check and see if we have 10 electrons. Right now we've got 12 electrons. That's still too many. So we're going to do this again. Take one pair off of each atom. It does not matter which ones. And I'm going to put another bond in instead. So another shared pair. This is a triple bond sharing 6 electrons. Everything still has its octet, and we have 10 electrons. So see the octet here. Each dash again is 2 electrons, so that's 8, and then an octet here as well. So normally when I'm done, I like to redraw this and make it look nice. So something like that for my final structure. All right, next we've got carbon dioxide. We're going to draw doubles before triples. We've written here in parentheses. This time we are going to have a central atom. Remember, carbon always goes in the center. Give everything its octet. So the carbon gets 2 lone pairs, and then the oxygens get 3 lone pairs. If I add this all up, I've got 20 electrons. Okay, how many am I supposed to have? Well, carbon's in group 4A, 4 valence electrons. Oxygen in group 6A, that's 6 valence electrons, times 2. That adds up to 16 valence electrons total. I've got too many in my structure, so I have to fix it. I'm going to take one pair off the carbon and then one pair off of either one of the oxygens. It doesn't matter. I'm going to do the one on the right, but then I have to make sure that I put my bond in between those 2 atoms that I took the electrons off of. This is so I can maintain that octet rule. Okay, so we add that all up again, and we've got 18 electrons. That's still too many. And then here's where drawing doubles before triples comes in. I'm not going to put a triple bond there instead of the double bond over on the right side. I'm going to put in another double bond on the left side. So one pair off of the carbon and then one pair off of the oxygen on the left side, and then put the double bond in there instead. So we've got 16 electrons. We've got an octet for everything. And again, I like to redraw this when I'm all done and make it look nice. Okay, so something like that. I'd like you to pause the video here and try to draw the Lewis dot structure for ozone, O3. This is what's in the ozone layer. We're going to draw this out as a straight chain, not a triangle. So we're never going to do any cyclic structures like this. Okay, we still want to have this idea of a central atom. And so take a moment, pause here, and try to complete that Lewis dot structure. Okay, so oxygen, 6 valence electrons times 3 is a total of 18 electrons. If I draw this normally and give everything its octet, including the oxygen in the middle with the 2 lone pairs, I once again will find that I have 20 electrons and I can only have 18. So we're going to modify this structure. One pair off of the central oxygen, and then pick an oxygen to take the other pair off of. I'm going to do this one. And so I've got my 18 electrons now instead of 20, and everything still has its octet. Now in the last example, I drew this Lewis dot structure for the ozone, but could I have drawn this one? Absolutely. So we say that ozone has resonance structures. So that these are structures where you can put a multiple bond, a double bond or a triple bond in multiple places. And so when we represent resonance structures, we draw them all out, and then we will put a double-headed arrow in between to kind of show that they are interchangeable. So at one time we used to think that the electrons would resonate back and forth between the two positions within the ozone. So that's why we call them resonance structures. However, now we actually think that the bonds are identical. And that's kind of hard to represent, so that's why we still use these resonance structures. So the identical bonds would kind of be like a bond and a half, and again, that's really hard to represent with a Lewis dot structure, so that's why we still use the resonance structures with single, double, or triple bonds. I'd like you to pause the video here and try to draw the Lewis dot structure for SO2, sulfur dioxide. Okay, sulfur 6, oxygen 6 times 2. Altogether, that is 18 valence electrons. So sulfur in the center. Give everything its octet. This is too many electrons. This is 20. So that's where multiple bonds come in. Take a pair off the sulfur, a pair off of one of the oxygens, and put in your double bond. I just as easily could have put the double bond on the right side, so there's another resonance structure to draw here. So it just looks like this with the double bond on the right side. So two resonance structures for SO2.